This homework was quite hard, but quite important as well, so I'm going to take some time to explain it now. The first question was about units in Z root 11. So we're looking for units in Z root 11. So we're looking for A plus B root 11 with A and B in the integers, such that the norm of this, so this is R, we want the norm of R to be 1, because remember you're a unit in Z root D, if and only if your norm is 1. R is a unit if and only if the norm of R equals 1. So what's the norm of this? Well, the norm of A plus B root 11 is the modulus of A squared minus 11B squared. So we want that to be 1. So basically the best way to do this is to do it by trial and error. And if you think about putting a square in there and a square in there, hopefully pretty soon by trial and error, you'll see that you could have 100 here and 9 there as your two squares. And if you subtract 11 times 9 from 100, you get 1. So we can put A equals 10 and B equals 3, because then the norm of 10 plus 3 root 11 is going to be 100 minus 11 times 9, which is 1. So that shows that this is a unit. So 10 plus 3 root 11 is a unit, and it's greater than 1. So it's greater than 1. Now what's the significance of it being greater than 1? Well, the next thing that you're asked to do in this question is to use this to show that the group of units of Z root 11 is infinite. And the point is that because this is greater than 1, you can keep multiplying it by itself and get different numbers. Now, you know that the group of units, well, you know that the units form a group, so if you multiply any two units together, then you definitely get another unit. So what we're saying here is that the units form a group so 1, R squared, R cubed, and so on are all units. And the significance of R being greater than 1 is that we know that these are all different. And R is greater than 1, so 1 is less than R. When you square them, that means they keep getting bigger. So they're all distinct. So that means that we've got an infinite number of them. Okay, so that deals with question 1. Question 2 was a bit different. It was about finding irreducibles in Z root minus 13. So if we look at Z root minus 13, this is question 2 now, and at the first place you're asked to show that there's no element of norm 2 or 11. So can we have an element? Can we have norm 2? Well, so what we're looking for, i.e., can we have, so what's the norm? We've got R equals A plus B root minus 13, where importantly A and B are integers. This is what makes the entire question go. It's the fact that A and B are required to be integers. So can we have that such that the norm, well, what's the norm of this? It's the modulus of A squared plus 13B squared. But of course, this is greater than or equal to 0, and so is that. So the modulus is just it. We can remove the modulus signs. So we want that to be equal to 2. So the first thing you say is that certainly b, if this is going to be true, b has got to be 0. Because if b was greater than 0, then you'd immediately get this whole thing being bigger than, greater than or equal to 13. So that wouldn't do. So we immediately need, we need b equals 0. Otherwise, a squared plus 13b squared is definitely going to be greater than or equal to 13. But if b equals 0, then that tells us that a squared equals 2. That implies that a squared equals 2. And that's a contradiction because a is an integer. Contradicts a being an integer. There is no integer whose square is 2. So we can't have the norm being 2. There is no element of norm 2, and similarly 11. Because if you try doing it for 11, you'll see that again, if that was greater, b was greater than or equal to 0, you'd immediately get this whole thing being greater than or equal to 13, which is bigger than 11. So b has to be 0, which means that a squared has to be 11, and that can't be true either. So we can't have anything in norm 11 either. Okay, so that deals with the first part. The second part was to show that if your norm is 4 or 22 or 121, then you're definitely irreducible. So if you're asked to show that something is irreducible, it's a good idea, first of all, to know what the definition of irreducible is, and then show that your thing actually satisfies it. So R irreducible means, first of all, R is not a unit, and second of all, that if R equals ST, then S is a unit or T is a unit. So in order to show that something is irreducible, first you have to check it's not a unit, and then you have to check that if it equals ST, then S is a unit or T is a unit. Okay, so suppose that the norm of R equals 4, right? So certainly it's not a unit because you're a unit if and only if your norm is 1. So certainly not a unit. Now what you have to show is that if R equals ST, then S is a unit or T is a unit. Now, so we suppose that R equals ST, and the aim is to show that either S is a unit or T is a unit, right? And we use the norms. So then the norm of R equals, we know that that equals the norm of S times the norm of T, right? But this equals 4. And we know that the norm of S and the norm of T do not equal 2. By the previous part of the question, that can't equal 2, and the norm of T can't equal 2. So the only other possibility, because 4 is 2 times 2, the only other possibility is that these equal 1 and 4, or 4 and 1. So we must have the norm of S equaling 1 and the norm of T equaling 4, or the other way around. But now we've got the result, because we have shown that either the norm of S is 1 or the norm of T is 1. And if the norm of S is 1, that means S is a unit. And if the norm of T is 1, then T is a unit. So this means that S is a unit. And this one here means that T is a unit. So we have shown that either S or T is a unit. So look again at how this went. Oh, there goes the timer, which means I've only got 30 seconds left to speak. So we said if R equals ST, then we worked our way through all this thing and showed that either S or T is a unit. And that's what you have to do to show that something is irreducible.